Our universe is a three-dimensional bubble expanding in a larger nirvana, a never-ending nirvana of 11-dimensional hyperspace. Spaces beyond human comprehension.
The Andromeda Galaxy, our stunning cosmic neighbor, has long captivated astronomers with its mysteries and potential. Despite its distance, the galaxy continues to be a focal point of cutting-edge scientific exploration. Esteemed physicist Michio Kaku, for instance, has reflected on how the James Webb Telescope has detected alarming signals from the Andromeda Galaxy. There's clearly much more to our galactic neighbor than what catches the eye. But why, despite so many challenges, do we continue to study Andromeda and the far reaches of space? Well, this is a journey that mirrors the historic leaps from flight to moon landings, proving that even the most distant dreams are often closer than we think. There's a lot to unfold today, so let's get started. Peering at the Andromeda Galaxy. In August 2022, the James Webb Space Telescope used its near-infrared camera to conduct an initial survey of Andromeda Galaxy's key regions. These observations aim to map star-forming molecular clouds and study interstellar dust with unparalleled detail. By capturing infrared light, JWST can peer through dense dust clouds that obscure visible light telescopes, offering unprecedented insights into Andromeda's hidden structures. Throughout its mission, JWST has continued targeting specific areas within Andromeda to uncover details about its star formation, the composition of its interstellar medium, and the dynamics of its spiral arms. These observations complement earlier studies by telescopes like Hubble and Spitzer, providing a more comprehensive picture of the galaxy's history and evolution. Esteemed physicist and futurist Michio Kaku seemed to believe that the JWST is set to unveil something amazing. But what could it be? Why bother with a whole other galaxy? This is one big ride, and there are a lot of shocking revelations too, so stick around as we unveil the mysteries of the Andromeda Galaxy, one by one. Let's start by understanding the instrument that makes it all possible. The James Webb Space Telescope, our eyes in the cosmos. The idea of a telescope in space, free from the atmospheric distortions of our planet, is nothing new. The Hubble Space Telescope allowed us to peer deeper than ever before into the farthest recesses of space in the 20th century. However, the Hubble could only make observations in the visible spectrum, thus limiting its abilities. Naturally, the concept for a successor began in 1996, when NASA, in partnership with the European Space Agency and the Canadian Space Agency, developed a space telescope capable of observing the universe in the infrared spectrum. The James Webb Space Telescope was designed to push the boundaries of astronomical observation further than ever before. Many key cosmic phenomena, such as the formation of the earliest galaxies, birth of stars, and planetary system evolution, are best observed in infrared wavelengths. Infrared radiation is emitted by cooler objects like gas clouds, young stars, and exoplanets, which are often hidden from view in visible light. With its ability to see through cosmic dust and detect faint, distant objects, JWST is shedding new light on cosmic mysteries, including the formation of the first stars and galaxies, the nature of exoplanets, and the potential for life elsewhere. The design and construction of the telescope make it one of the most sophisticated observatories ever made. The mirror, for example, is made of 18 hexagonal segments of gold-coated beryllium, spanning an impressive 6.5 meters in diameter, nearly 3 times the size of Hubble's primary mirror. The JWST is also equipped with a sunshield, which consists of 5 layers of a special material called Captain, designed to block the heat and light from the Sun, Earth, and the Moon. This ensures that the telescope's instruments remain at the extremely low temperatures necessary for infrared observation. The sunshield is about the size of a tennis court, and it plays a vital role in keeping the telescope's infrared detectors cool, as the telescope operates at around -223 degrees Celsius. The limitations of Earth-based observations have been a significant driver behind the development of JWST. While ground-based telescopes, including the Very Large Telescope in Chile or the Keck Observatory in Hawaii, have provided remarkable insights into the universe, they are fundamentally limited by Earth's atmosphere. The Earth's atmosphere absorbs and distorts a significant portion of the electromagnetic spectrum, especially in the infrared, which is essential for observing distant, faint, or obscured objects. This phenomenon is called atmospheric interference, and it severely limits the capability to observe celestial phenomena like the birth of stars or distant galaxies, as well as the atmospheres of exoplanets. To overcome these limitations, the JWST was placed in a unique orbit around the second Lagrange point, or L2, about 1.5 million kilometers or 1 million miles from Earth. This orbit provides a stable environment for the telescope, free from the turbulence of Earth's atmosphere, and allows it to observe the universe with unparalleled clarity. The location also ensures that the telescope remains shielded from the heat and light of the Sun and Earth, maximizing its ability to detect faint infrared radiation from deep space. JWST's infrared sensitivity allows it to peer into dusty regions where stars are forming, study the early universe, and even observe distant galaxies that formed just after the Big Bang. Its suite of advanced instruments, including the Near-Infrared Camera, or NIR-CAM, the Mid-Infrared Instrument, or MIRI, and the Near-Infrared Spectrograph, or NIR-SPEC, work together to provide high-resolution imaging and spectroscopy across a wide range of infrared wavelengths. These instruments allow astronomers to study the physical properties of distant galaxies, stellar nurseries, and even exoplanets, providing insights into their composition, temperature, and structure. With such capabilities, the JWST can peer into distant galaxies, such as Andromeda, in unprecedented detail. Previous observations of Andromeda, including the detection of X-rays and the PA99N2 microlensing event, were limited by the observational capabilities of previous space telescopes, like Hubble and ground-based telescopes. However, this is all set to change. So, what do we know about the Andromeda Galaxy, our cosmic neighborhood? The Andromeda Galaxy, also known as Messier 31 or M31 or NGC 224, is a barred spiral galaxy and the closest major galaxy to our own Milky Way. Nestled approximately 2.5 million light-years from Earth, its immense scale and rich history have made it a cornerstone in our understanding of galactic dynamics and evolution. The Andromeda Galaxy boasts a diameter of approximately 152,000 light-years. Regarding its mass, early estimates suggested it was 25 to 50% more massive than the Milky Way. Modern studies, however, indicate the two galaxies might have more comparable masses. In fact, our Milky Way may be more massive. Andromeda's name originates from the constellation where it is found, named after the mythical Greek princess Andromeda, wife of Perseus. With an apparent magnitude of 3.4, Andromeda is one of the brightest deep sky objects, visible to the naked eye on clear, moonless nights, even from moderately light-polluted areas. The earliest recorded mention of Andromeda dates back to 964 CE, when Persian astronomer Abd al-Rahman al-Sufi described it as a small cloud in his Book of Fixed Stars. It later became known as the Little Cloud on medieval star charts. In 1612, German astronomer Simon Marius provided one of the earliest telescopic descriptions, although Charles Messier catalogued it as M31 in 1764. In the 18th century, William Herschel noted a reddish hue at Andromeda's core and estimated its distance at just 18,000 light-years. Of course, this underestimation was a result of the observational limits of the time. By 1850, William Parsons, the third Earl of Rosse, sketched Andromeda's spiral structure. In 1864, William Huggins observed Andromeda's spectrum, identifying stellar characteristics rather than those of a gaseous nebula. This marked a turning point in understanding Andromeda as a galaxy rather than a nearby nebula. A major milestone occurred in 1885 when the supernova S Andromeda was observed in the galaxy, the first and, to date, only recorded supernova in Andromeda. The first photograph of Andromeda, taken by Isaac Roberts in 1888, further advanced understanding of its spiral structure. Roberts mistakenly believed it to represent a stellar system in formation, a view that was corrected as astronomy progressed. In 1912, Vesto Slipher measured Andromeda's radial velocity using spectroscopy, finding it to be approaching the solar system at a then-record speed of 300 kilometers per second. Yes, you heard that right. Andromeda and the Milky Way are on a collision course. Well, more on that later. For now, let's move forward with our walk through history. X-rays detected. By the late 1960s, the Andromeda Galaxy had eluded X-ray detection despite advances in observational technology. This posed questions about the galaxy's high-energy processes. However, on October 20th, 1970, a pivotal balloon flight experiment set an upper limit for detectable hard X-rays from Andromeda. These early efforts highlighted the limitations of existing equipment, but laid the groundwork for future missions capable of probing the galaxy's energetic phenomena. In a major breakthrough, the Swift Burst Alert Telescope All-Sky Survey detected hard X-rays originating from a region centered just 6 arcseconds from Andromeda's galactic center. The emission, measured at energies above 25 kilo-electron-volts, was traced to a single source. This is a relatively small amount of energy on human scales, but significant on atomic and subatomic scales. For context, X-rays usually range from about 100 electron-volts to 100 kilo-electron-volts in energy. A 25 kilo-electron-volts X-ray would fall into the category of soft X-rays, meaning they are lower in energy compared to the more penetrating hard X-rays. Medical imaging systems often use X-rays in the range of 15 to 30 kilo-electron-volts, as these energies provide good contrast for imaging soft tissues. However, when discussing cosmic phenomena, X-ray observations often deal with sources emitting in the kilo-electron-volts range. For instance, hot gases near black holes or neutron stars can emit X-rays with energies of 10 to 50 kilo-electron-volts, and studying them reveals information about extreme environments, such as temperatures in the millions of degrees. In the case of Andromeda X-ray emissions, further analysis revealed the source to be a binary system where a compact object, either a neutron star or a black hole, accretes matter from its stellar companion. As the compact object siphons gas, the material heats to millions of kelvins, emitting powerful X-rays as it spirals toward the accretion disk. This discovery not only confirmed the presence of high-energy processes within Andromeda, but also demonstrated the precision of modern X-ray observatories in resolving point sources within a galaxy's core. Subsequent observations by the European Space Agency's XMM Newton Orbiting Observatory uncovered numerous X-ray sources scattered across the Andromeda Galaxy. Many of these sources can be black holes or neutron stars actively accreting matter. Differentiating between neutron stars and black holes primarily relies on mass measurements, with neutron stars typically having masses between 1.4 and 2.1 times that of the Sun, while black holes exceed 3 solar masses. Observations by NASA's Nuclear Spectroscopic Telescope Array, or NuSTAR mission, further expanded the catalogue of these compact objects, identifying 40 such X-ray emitting sources. In 2012, we came across a microquasar, which is a smaller-scale analogue of quasars, characterized by jets powered by a stellar mass black hole. This was detected near Andromeda's galactic center. With an estimated mass of around 10 solar masses, the progenitor black hole was identified using data from the European Space Agency's XMM Newton Observatory and corroborated by NASA's Swift Gamma-ray Burst mission and the Chandra X-ray Observatory. Ground-based facilities such as the Very Large Array, or VLA, and Very Long Baseline Array, or VLBA, provided additional support, enabling detailed study of the microquasar's radio bursts and jet dynamics. This microquasar was the first observed within the Andromeda Galaxy, and the first detected outside the Milky Way. The cumulative discoveries of X-ray sources in Andromeda illustrate the galaxy's complex interplay of gravitational forces, high-energy physics, and stellar evolution. These compact black holes and neutron stars allow us to understand the extremes of matter and energy. Upcoming missions, like the Athena X-ray Observatory and next-generation ground-based facilities, promise to refine mass measurements of compact objects, detect fainter X-ray sources, and explore the galaxy's population of intermediate-mass black holes. As our observational capabilities grow, the Andromeda Galaxy will allow us to advance astrophysical theories. Speaking of advancing our understanding, we came across a major shock back in 1999. The PA99N2 event. The PA99N2 microlensing event in 1999 marked a significant milestone in the study of high-energy astrophysics and exoplanetary research. This event, detected within the Andromeda Galaxy, caught the attention of astronomers due to its potential implications for the existence of exoplanets beyond our Milky Way. Microlensing occurs when a massive object, such as a star or planet, passes in front of a more distant background source, bending and magnifying its light due to gravitational lensing. In the case of PA99N2, the event was interpreted as the gravitational lensing of a red giant star in the Andromeda Galaxy by a foreground star with a mass estimated between 0.02 and 3.6 times that of our Sun. This discovery sparked interest in the possibility that the foreground star was accompanied by a planet, well, an exoplanet orbiting a star located in another galaxy. This relatively small star was surrounded by an object exerting a significant gravitational influence, consistent with the presence of a planet. What made this particular candidate even more compelling was the mass estimation of the potential exoplanet. The inferred planet was believed to be 6.34 times the mass of Jupiter, placing it in a class of exoplanets known as super-Jupiters. The name itself speaks volumes about the size and enormity of such exoplanets. Super-Jupiter are massive. Gas giants that, though similar to Jupiter in composition, can be much larger in mass and size. If confirmed, this would have been the first exoplanet ever discovered outside the Milky Way. This was a groundbreaking achievement in the search for planets beyond our galaxy, and an unprecedented step toward understanding exoplanetary systems in other galaxies. However, while the initial excitement surrounding PA99N2 was palpable, anomalies soon emerged in the data. After further analysis, astronomers identified inconsistencies that raised doubts about the original interpretation of the event. Microlensing events are often subject to complex variables, including the alignment of the objects involved, the potential for multiple foreground objects, and the ability to distinguish between a lensing event caused by a star and one caused by a planet. These factors can introduce uncertainties in the mass estimations and the nature of the lensing object. One key issue was the detection of additional features in the light curve of the event, which suggested that the object causing the lensing might not have been a single star, as initially assumed. Instead, the data hinted at the possibility of multiple lensing objects, or a more complex lensing configuration. This discovery led some astronomers to question whether the event truly indicated the presence of an exoplanet, or if the observed anomalies were due to other astrophysical phenomena. Despite the eventual doubts surrounding the PA99N2 event, the detection of a possible exoplanet in Andromeda remained an important step in extragalactic research. It also highlighted the potential of microlensing to uncover planets in distant galaxies, offering a glimpse into the vast diversity of planetary systems beyond the Milky Way. The study of extragalactic exoplanets presents unique challenges, particularly due to the immense distances involved and the difficulty in observing faint objects in other galaxies. However, the PA99N2 event emphasized that the search for such planets could yield valuable insights into the prevalence and characteristics of planets in different galactic environments. The event also set the stage for future discoveries in this exciting field. Advances in observational technology, particularly in space-based telescopes such as the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope, promise to provide much greater sensitivity and precision in detecting and analyzing microlensing events. In addition to improved observational tools, further refinements in data analysis techniques will enhance our ability to distinguish between the many factors that can contribute to microlensing events. By combining gravitational lensing data with other observational methods, such as spectroscopy and astrometry, astronomers will be better equipped to confirm the existence of exoplanets in distant galaxies and explore their physical characteristics. The PA99N2 microlensing event, though not without its uncertainties, represented a pioneering moment in the quest to identify exoplanets beyond the Milky Way. But wait, that's not all we know about the planet. There's at least one more detail that has us on the edges of our seats. The Andromeda Galaxy is going to collide with the Milky Way. Yes, this is no exaggeration or hyperbole. The Andromeda Galaxy is indeed slowly, but inexorably drawing closer to the Milky Way. Esteemed physicist Michio Kaku has also discussed the impending collision between the Milky Way and Andromeda galaxies on multiple occasions. For instance, in a tweet dated January 27, 2019, he stated, "The Milky Way galaxy will die when it collides with the Andromeda Galaxy, forming a gigantic elliptical galaxy and a giant black hole." Additionally, in a Facebook post, he referenced astronomers' observations confirming this future collision. He is spot on with his predictions. As the Andromeda Galaxy races toward us at a velocity of around 110 kilometers or 68 miles per second, it marks the beginning of a celestial event that will unfold over billions of years. Current measurements show that Andromeda is one of about 100 observable blue-shifted galaxies whose light is compressed by the gravitational pull between the galaxies, signaling a direct approach. The motion of the Andromeda Galaxy and the Sun's own motion through space are interconnected, as the Sun orbits the center of the Milky Way at a speed of about 225 kilometers per second. The combined velocities of the galaxies in relation to each other provide a fascinating glimpse into the future dynamics of these two galactic giants. The blue shift observed in Andromeda's light is a key feature that distinguishes it from the vast majority of galaxies, which are generally red-shifted due to the expansion of the universe. Blue shift occurs when a galaxy moves toward the observer, causing the wavelength of its emitted light to shorten, shifting toward the blue end of the spectrum. This is the opposite of redshift, where light from receding galaxies stretches into longer wavelengths. The blue shift of Andromeda, therefore, indicates that it is moving directly toward the Milky Way. This is a rare but significant phenomenon, and it gives us a clear indication that the two galaxies are not just passing by each other, but are on a collision course. Current projections suggest that the Andromeda Galaxy will collide with the Milky Way in about 2.5 to 4 billion years. This long timescale is a cosmic eternity in human terms, but in the life of galaxies, such events are not rare. Galactic collisions are relatively common in the universe, especially in galaxy groups like the Local Group. In fact, the Milky Way and Andromeda are already gravitationally interacting, with each galaxy's gravity pulling at the other in a gradual but inevitable cosmic dance. When these two giants collide, they will merge to form a single, much larger galaxy. This new galaxy could take the form of a giant elliptical galaxy or possibly a large disk galaxy, depending on the dynamics of the collision and the angular momentum of the two parent galaxies. Elliptical galaxies are typically formed from such mergers due to the chaotic nature of the collision, which can disrupt the orderly structure of the galaxy's stars, gas, and dust, resulting in a more spherical shape. However, there remains a chance that the merger could lead to a large disk galaxy, albeit with a much different structure than the current Milky Way or Andromeda. One of the critical outcomes of the merger will be the rearrangement of stars, gas clouds, and other matter. While individual stars within the galaxies are unlikely to collide directly, the gravitational forces at play will lead to significant changes in their orbits. New star formation could be triggered by the compression of gas clouds, leading to bursts of starbirth in certain regions. At the same time, other stars may be ejected from the merged galaxy entirely, some even escaping the gravitational influence of the new galaxy. Perhaps the most intriguing question in the scenario of the Milky Way-Andromeda collision is the fate of the solar system. The current scientific consensus is that while the solar system will likely not be directly impacted by the galactic merger, the gravitational forces involved could dramatically alter its trajectory. There is a small but significant possibility that the Sun and its planets could be ejected from the Milky Way galaxy altogether. Such a scenario would mean that the solar system would become an isolated rogue system, floating through intergalactic space, no longer bound by the gravitational pull of the Milky Way or Andromeda. Alternatively, it's possible that the solar system could be drawn into the newly formed Andromeda Milky Way galaxy. In this case, the solar system could become part of a different galactic structure, possibly altering its orbit within the galaxy. It's important to note, however, that these changes would happen on timescales far beyond the lifetime of the Sun, which is expected to exhaust its nuclear fuel and evolve into a red giant in around 5 billion years. Thus, the solar system's fate may ultimately be determined by the Sun's life cycle before the galactic collision even occurs. If the solar system remains within the newly merged galaxy, Earth's position relative to the galactic core may change, altering the environment and conditions of our home planet. This could result in new cosmic influences on our star, but whether such changes would have a direct impact on life on Earth is still unclear. Collisions between galaxies are not rare occurrences in the universe. In fact, most galaxies that exist today have undergone or will undergo a similar process at some point in their cosmic history. The merger of the Milky Way and Andromeda is simply one of the most prominent examples, as both galaxies are relatively close to us, and their collision is inevitable. Large galaxy groups like the Local Group are often composed of multiple galaxies bound together by gravity, and interactions between these galaxies are frequent. Over time, these interactions lead to the merging of galaxies, reshaping the structure of the local universe. Despite the destructive forces at play during such collisions, galactic mergers can be a source of new star formation and evolution, giving rise to entirely new cosmic structures. The merger of the Milky Way and Andromeda will reshape the local universe and may even have profound implications for the formation of new planetary systems. Some astronomers speculate that the events triggered by the merger could result in the formation of new star clusters, and in the far future, even the emergence of new exoplanets within the merged galaxy. So, what does the big man have to say about all of this? Well, let's find out. Michio Kaku's take on the Andromeda Galaxy and the JWST, renowned theoretical physicist and futurist, Michio Kaku has been vocal about the groundbreaking potential of the James Webb Space Telescope, particularly regarding its capacity to uncover new details about galaxies, including our neighboring Andromeda Galaxy. In an interview with Fox News in 2022, Dr. Kaku expressed his enthusiasm for the telescope's ability to peer into the distant universe, offering a unique opportunity to understand phenomena that have eluded scientists for decades. He described the JWST as the most powerful telescope ever built, and emphasized that its infrared capabilities would allow it to observe galaxies formed just a few 100 million years after the Big Bang, thereby opening a new window into cosmic history. Dr. Kaku further discussed how the JWST's findings are already challenging existing theories of galaxy formation and evolution. For example, the telescope's observations of distant galaxies like Glass Z13, which appears to have formed only 300 million years after the Big Bang, have led scientists to reconsider their models of early galaxy growth. This discovery, as Dr. Kaku noted, suggests that galaxies formed much earlier than initially expected, calling into question established assumptions about the timeline of the universe's development. He also highlighted that the JWST's advanced infrared sensors could provide unparalleled insights into such nearby galaxies. The telescope's ability to see through dust clouds and observe otherwise hidden regions, such as the central bulge of the Andromeda Galaxy or the supermassive black hole at its core, could revolutionize our understanding of its structure and dynamics. He also speculated that the JWST might unveil more details about the interactions between Andromeda and the Milky Way, especially given the predicted collision between the two galaxies in around 2.5 to 4 billion years. Moreover, during his appearance on the Infinite Monkey Cage podcast in 2021, Dr. Kaku elaborated on how the JWST might refine our understanding of cosmic phenomena across a wide range of scales. He pointed out that the telescope's ability to study not just distant galaxies, but also individual stars and even exoplanets would enable scientists to test theories of star formation, planetary systems, and the conditions for life. His comments underscored the potential of JWST to reshape not only our knowledge of the universe's past, but also our understanding of the future of space exploration and technology. Overall, he has exhibited a deep optimism about the telescope's potential to expand the boundaries of human knowledge and understanding of the universe. But why should we care? How does it affect us? Well, let's answer this. Why bother with Andromeda? Exploring space and venturing toward distant celestial bodies like the Andromeda Galaxy may seem daunting, considering its vast distance from Earth. At first glance, investing so much effort into exploring such remote reaches of the cosmos can feel wasteful, especially when intergalactic travel seems beyond our current technological capabilities. However, a closer look at humanity's history reveals that every monumental leap we've made in exploration has been marked by seemingly insurmountable challenges, each of which laid the foundation for the next great breakthrough. The journey from controlled flight to landing on the moon is a perfect analogy for how space exploration, even at the farthest corners of the universe, may be our stepping stone to intergalactic travel and colonizing other planets. Space is the final frontier, and by exploring it, we are not only seeking to answer profound scientific questions about the origins of the universe and our place in it, but also to safeguard the long-term future of humanity. As our planet faces increasing challenges, such as climate change, resource depletion, and potential existential threats like asteroid impacts or nuclear war, the idea of extending human civilization beyond Earth is gaining momentum. The exploration of the Andromeda Galaxy specifically, while millions of light-years away, offers the possibility of understanding galactic evolution, the potential for life elsewhere, and the fundamental forces that govern the universe. Even though we currently lack the technology for direct intergalactic travel, studying distant galaxies is a key to unlocking the mysteries of space that will shape the future of human exploration. Just as the leap from controlled flight to landing on the moon seemed insurmountable at the time, the path to intergalactic travel and colonizing distant planets may appear similarly distant. However, these two feats share a common thread: the relentless pursuit of progress in the face of seemingly impossible odds. Consider the timeline of human flight. In 1903, the Wright brothers achieved the first controlled, sustained flight with their flyer at Kitty Hawk, North Carolina. This groundbreaking achievement took place just 66 years before humanity landed on the moon in 1969 during the Apollo 11 mission. The Wright brothers had no idea that their flight would one day lead to rockets capable of reaching the moon. What followed were decades of rapid technological advancements in aviation and space exploration. The Apollo 11 mission, spearheaded by NASA, was the culmination of decades of scientific research, engineering, and the collective ambition of humanity. In this same vein, the study and exploration of distant galaxies, such as Andromeda, may seem abstract and impractical today, but the knowledge we gain from these missions will provide the foundation for the next phase of human space exploration: intergalactic travel. The advances made through technologies like nuclear propulsion, advanced AI for navigation, and even theoretical concepts like warp drives could pave the way for journeys beyond our galaxy. Technologies developed for deep space exploration may one day evolve to the point where traveling to nearby star systems, or even galaxies, becomes plausible. Space, after all, is the final frontier. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.